All right, so if you've been battling your way through differential equations, you know the Laplace transform is an absolute game changer. But what happens when you run into equations that go beyond second order? Well, today, we're pushing this amazing tool to its limits to see how it makes even the most intimidating, higher-order problems totally manageable. Let's get into it. Okay, so you've probably got second-order equations down. No sweat, right? But what happens when the game gets harder? A third order? A fourth? What if you see some crazy nth-order derivative? Does the whole method just fall apart? Well, as you're about to see, the answer is a big, fat no.
And look, this isn't about learning some brand new, complicated technique. It's really about leveling up a skill you already have. We're just extending the power of the Laplace transform from that familiar territory of second-order problems to help us conquer these new heights.
And you want to know the best part of all this? There are no new complex rules you have to memorize. Seriously, if you get how to transform a second derivative, you've already done all the hard work. The rest? Well, it's just about spotting a really simple, elegant pattern.
So, what is this magic pattern? Let's pull back the curtain and break down the master formula that unlocks everything, taking us from any derivative, I don't care what the order is, straight into the much friendlier algebraic world of S.
Let's start on some familiar ground. This right here is the Laplace transform of a second derivative. You've probably used it a bunch of times. Just take a second and notice the structure. You've got an s-squared term multiplying your transformed function, y of s, and that's followed by terms that involve your initial conditions, y of 0 and y prime of 0. Keep that structure locked in your head.
And here it is, the general formula for an nth-order derivative. Now, okay, deep breath. Don't let the notation freak you out. Let's just break down the beautiful pattern here. The first term is always s to the power of n, whatever your derivative order is, times y of s. Easy enough. From there, look what happens. The power of s just decreases by 1 in every single term, s to the n minus 1, s to the n minus 2, all the way down. At the exact same time, the derivatives of our initial conditions are increasing in order. First y of 0, then y prime of 0, all the way up to the n minus 1th derivative. See? It's just a perfectly predictable progression.
Theory is cool and all, but let's see how this actually plays out in practice. We're going to walk through 3 different examples that really show off just how powerful and versatile this formula is. First up, a classic third-order initial value problem. We've got the third derivative of y minus y equals 0. And since it's a third-order equation, we're given all 3 initial conditions we need to get the job done: y of 0, y prime of 0, and y double prime of 0.
So, what's our game plan to solve it? It's pretty straightforward. First, we apply our new general formula to that third derivative. Step 2, we plug in all those initial conditions they gave us. After that, it's just algebra. We group up our terms and we solve for y of s. And that last step just gets us ready to find the inverse transform. And boom, here's what you get. After we apply the transform and plug everything in, we've turned that whole differential equation into this single algebraic expression for y of s. The calculus is done. Seriously, all that's left is a good old-fashioned algebra problem, using partial fractions to get the inverse transform.
Now, this technique isn't just for abstract math problems you find in a textbook. This fourth-order equation, for instance, is super common in mechanical and civil engineering. It's actually used to model how beams bend when you put a load on them. And even for a fourth-order problem like this, the exact same principle applies.
Okay, now for an example where the Laplace transform isn't just helpful, it's pretty much a lifesaver. Take a look at the right-hand side of this equation. u5 of t. That's a Heaviside step function. All it means is that we have a forcing term that suddenly switches on. And trust me, these kinds of discontinuous problems are usually a total nightmare to solve with other methods.
And I'm really not exaggerating when I say a nightmare. The source material puts it bluntly: trying to solve this using a method like variation of parameters would be, and I quote, an absolute nightmare. It would just be an incredibly long and messy process. But with the Laplace transform, that difficult discontinuous function on the right, it just becomes this simple, clean algebraic term, e to the minus 5s over s. And that's the whole point. We've once again turned a very hard calculus problem into a straightforward algebra problem. This is exactly where the method really, truly shines. So let's wrap this all up. What you've just unlocked is basically a secret weapon. It's a systematic way to convert any linear, constant coefficient differential equation, no matter how high the order,
from the complicated world of calculus into the much, much friendlier world of algebra. So, let's just recap the big takeaways here. First, transforming higher-order derivatives isn't scary. It just follows a simple, predictable pattern. It's just an extension of what you already know. Second, the whole point of this transform is to turn difficult calculus problems into manageable algebra. And finally, and this is a big one, this method is an absolute beast for handling those tricky, discontinuous problems that it just eats for breakfast.
So I'll just leave you with this question to chew on. You now have a tool that can systematically simplify derivatives of any order, which gets rid of one of the biggest headaches in solving these complex equations. So what's that one tough problem that you're now ready to go out and crush?